This is going to be a very brief, a whirlwind intro to random variables with the target of getting it into the calculus setting, but I wanted to do a discrete example of a couple of concepts. So it's going to be a situation where we have a game played with one die, a six-sided die, but it's loaded, so it's unbalanced, so that it has different probabilities. It's not just 1 out of 6 to get each of the values, and the probability of rolling a 1 is going to be 0.1. Probability of rolling a 2 is going to be 0.05, even smaller. Probability of rolling a 3 is, let's say, 0.15. Probability of rolling a 4 is 0.2. Probability of rolling a 5 is 0.4. That's quite likely, comparatively. And the probability of rolling a 6 is 0.1. Now, notice you should do a double check here. Already, if I'm claiming that's all the possibilities, then there's something that has to be true about all these numbers. These probabilities have to add up to 1, because the probability that something happens is always going to need to be 1. That's going to be a very important principle. Now, here's the thing. When we talk about probability and specifically random variables, I can label these different events by the values of a quantity, namely what is the die roll. And so what I can do is I can let x, and you usually let a capital letter indicate what's called a random variable. This is essentially the outcome of an experiment. It's not really standing for a number so much as a bunch of different numbers that have come out of the same experiment. So let x be the die roll, the number that shows up on that die. And then so what we're really saying is the probability that that random quantity equals a certain value is 0.1. And similarly, the probability that that random quantity equals 2 is 0.05. And then we could put that in the same way here. And this is called a random variable, some sort of quantity that has a numerical value, but that is generated in some random way by some sort of experiment. And then we ask questions about what happens if we do this over and over again. Is it more likely to do one thing or another? On average, what happens? And so this is a good example of a random variable. Now, this is a discrete random variable because it is only ever taking these 6 values. It never takes 1.1, it never takes e or pi or root 2 or anything like that. And in calculus, we're going to be looking at continuous random variables that maybe could take any value in between 1 and 6. But you usually want to start with discrete random variables. So there's a good way to picture this, which is we can make a chart of all these values. And if you've ever seen a histogram, it's very similar to a histogram. And that is to put an x here, and I'm going to put a little x. When we use a little x in this situation, we're saying a possible value. This really does stand for a number. Some possible value of this machine that gives you the results of experiments, basically. So it's a possible value of the random variable, and the possible values are 1, 2, 3, 4, 5, 6. And then we can put a bar, or we could just put a dot. I'll put bars to indicate the probability of getting each of these. So let's see, 0.4, that's going to let's make 0.4 over here. So to get a 5, that's going to be 0.4. Let's see, there's the one just ahead of that is half, that's 0.2. The one ahead of that is like 3/4 of that. Actually, let me not make these connect, because I'm just making them bars so that they're pretty visible. But I don't want to suggest you can actually get anything in between, because you can't. Let's see, 0.05, let's see, so 0.1 was like this, just doing it roughly. 0.05 is like this, and then back to 0.1 is like this. Okay, so this gives us a visual picture of what the probabilities are. So these are the probability values of getting all these different values. Now, I have to say, when we go to continuous random variables, we're going to be talking about something called a probability density, and the y-axis cannot be directly interpreted as a probability. Just to warn you about that, I talk about that in my continuous probability videos, but this is here is a situation where we really can read them off as exact probabilities. Okay, so this is the kind of picture you want to have, and just from this picture, you can get a lot of information. You can say, okay, 5 is the most likely event. The most likely value of the variable is the way we're going to say it. Most likely value for for X to show up with after one of these experiments, one of these die rolls. And 2 is the least likely value. And then we can start asking questions like, well, on average, what are we going to get? And that would be called the mean or expected value. So we would say on average, or in the mean, what do we expect X to be? And it's not just going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6 all over 6, because that doesn't take into account the fact that 5 is much more likely and 2 is much less likely. We would hopefully expect that somewhere above the ordinary average of these 6 numbers would be where the actual average outcome would be, because it's loaded in a way that these higher numbers, especially 5, tends to be much more likely. So how do we calculate that? Well, one way we could do that, and really kind of a good definition of this, is just roll the die 1,000,000 times, get all those list of 1,000,000 numbers, and average those in the ordinary way. Well, we don't want to do that, but we can have a pretty good prediction of what the proportional spread of those out of those 1,000,000 rolls is going to be. About 40% of those 1,000,000 rolls are going to be 5s, and 20% are going to be 4s, and 5% are going to be 2s. So when we average all of those values, we're going to get 5s represented with a weighting that is based on the probability. And we're going to get many fewer 2s, but they're going to be present with a weighting based on the probability. So what we get is just a weighted average, exactly like taking an average of grades with like quizzes and tests and homework that are weighted differently. So we're just going to get a weighted average of the values of X, all the possible values of the random variable X. And so it's going to be 1 times the weighting 0.1 plus the possible value 2 times the weighting 0.05 plus 3 times that weighting was, look at my little sheet, 0.15 plus 3 times plus 4, just kidding, times 0.2 plus 5 times the big one, 0.4, plus 6 times back to somewhat small 0.1. And on my other window here, I have that calculated out, and it turns out to be 4.05. That's a bit bigger than the average of 1 through 6. If you actually take just the straight up average of 1 through 6, it's 3.5. And so there's a bit of a weighting. It's not drastic, but there's a bit of a weighting that says, on average, we're going to see more than the regular average of these numbers is going to be 4.5. So this is this is exactly actually 4.05. Okay, so in general, it's going to be a sum of X values times weights. Then those are just the probabilities. Okay, ooh, that's about as far down as I want to go. Okay, so, and I want to show you there's this idea of the expectation. This is also called the expectation value of X. So this would be often called like X bar for the mean of X. So you can't really see that. So this is going to be, we can take out the calculation. This is sometimes called X bar for the mean of X, or the expected value, capital E, of the random variable X. And it's called the expectation or expected value of this variable. And the cool thing is there's a lot of other variables we could base on this variable. And we might ask for, on average, what would we expect those to be? So a very common case would be, I describe this as a game, but so far it's pretty boring. You just roll this weird die that's not very fair, and you just stare at it. Well, it's always more interesting if you involve like winnings or money. What if the rules of the game are when you roll the die, then you win the square in dollars, let's say, it's a pretty rich game, the square of X of that die roll you see. Now you'd want to know, on average, what's this going to win you? So for example, somebody could say, I'm going to charge you $100 flat out to play this game. But then you could win quite a bit of money. Actually, no, that's kind of ridiculous. We don't want to do that. Let's say $20. Say it's a $20 charge to play the game, but you could win a bunch of money. You could win as much as $36. And is it a good idea to play this? And especially, is it a good idea to play it over and over again? Because every time you play, you're going to be guaranteed to be out $20. But if on average you win more than $20, this might be a really good idea. Okay, so once again, we're going to take this quantity. It's based on the random variable we're seeing here, but it's just you put that into some sort of function here, just squaring, and we can take the same kind of expected value. 1/10 of the time, you are going to win $1². 1/20th of the time, you are going to win $2². You're going to win $3². This was the 0.15, 15% of the time. And 20% of the time, you're going to win $16. And 40% of the time, you're going to win $25. That's pretty good. That's looking promising. Okay. And what? Don't want to get any further down than that. My little reminder of where to stop is not. It's a little messed up today. Okay, but hopefully that's okay. And I have that calculation right here. Okay, it turns out that on average you're going to win $18.45. So if they charge you $20 for this game, well, surprise, surprise, the house has a certain percentage. On average, they're going to it's going to be better. It might look tempting because almost half the time you're winning $25. That would get you $5 up, and 1/10 of the time you're winning $36. But on average, that's going to get sunk by the fact that there's a fair number of times when you win $1 or $4 or $9, and that $20 charge is really not making you happy at that point. So that's all I want to say for this video. But just we have this idea of some sort of quantity that can have various values with various probabilities. We make a plot of it that's essentially a histogram of those values. And then we can do things like the average, or more generally the expected value of any function of that random variable. Ooh, the last thing I want to say though, don't want to make it too long, but this really needs to be said. There's a great analogy here if you have some intuition with centers of mass. So if you make a physical rod, like a really lightweight rod, like lightweight plastic, and then you put like a bead on it here with mass equal to this probability, that was 0.1. And then here's a little bead with 0.05. Let's say this is kilograms. So 1/10 of a kilogram, 20th of a kilogram. Here, a bit bigger, 0.15, etc. Here's the really big one. Let me make it look a little bigger. 0.4, and you make these and you put them in exactly x position 1, 2, 3, 4, 5, 6 carefully with the correct masses, and you ask, where is this going to balance? Well, it turns out that calculation, again, I'm getting too low. I gotta fix that. The calculation that was the original calculation, the center mass was 4.05. That's exactly that expected value or average or weighted average, weighted by the probabilities. That's why they call it a weighted average, because literally it's where this bar would balance if you put these weights on, and that's the average position of those weights weighted by, in this case, the probabilities. So there's an exact correspondence between the math of the center of mass of a bunch of weights along a rod and the center of mass and the average value of a random variable with a certain probability distribution.